Okay, we're back at it, and we're going to talk more and 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 more of pH probes and pH meters. Isn't that exciting? I know that you're looking forward to it, just like I'm looking forward to discussing it. Well, that's kind of why I do my sound effects and my crazy analogies and everything else that you're going to experience throughout the entire time while you're in this course. All right, so this is where we left off, and we left off at this thing called a pH electrode, and we said that that electrode is really something called an ISE, and ISE means ion selective electrode. And there are tons of ISEs on the market. There are tons of different ISEs that I could use in a laboratory. And the pH one, or the hydrogen ISE, is one of many. But it's also the most common of many. And that's why we talk about this. That's why we discuss this first. Most of the time when we're using some type of probe, it's going to be pH related, if not pretty close. So again, depending on the company that I work for, depending on the industry, so for example, environmental industry, they might use all kinds of ISEs, right? But a pharmaceutical industry might use mainly pH meters. You just don't know until you actually get there, begin to work, and see what types of tests that they do. So we said that this ISE is called the working electrode for the measuring device, and the measuring device here is going to be our hydrogen concentration. All right, so that is what does the measuring. All right, so I'm going to write that on this old note. So the working electrode is the one that does all of the measuring, folks. The reason that I say this is because how is a galvanic cell made? A galvanic cell is made into two halves, a half cell and a half cell. One's reduction, one's oxidation. There's electron transfer, all kinds of new terms that I can use to make me sound really, really smart. But one of them, one of the half cells, will be the direct measuring device. And those are typically what we call the working electrodes. And in this particular case, it is meant to measure hydrogen. That is called the ISE. Now, just like with everything else in a lab, there's always going to have to be a reference point, right? I mean, things can't be done without a reference. So, for instance, I want you to think of an analytical balance, all right? When we had an analytical balance and we were using that, there was this pan that was up on top, right? So, with that analytical balance, I put something on top, I measured it, gave me a number. How? Right? How did it give me a number? How did it know that that was 10 grams or 5 grams or 1 gram? Well, we talked about that, right? We said, well, one of the ways that we do that is with calibration. And we have calibration weights that we can put onto the balance pan to double check it's giving me the proper number. And if it's not giving me the proper number, there's an internal calibration that it does. So it tries to reset itself every time, and it tries to, tear it out in a way. It says this is 20 grams, and this is what 20 grams is supposed to weigh. So I'm going to give you 20 for this kind of measurement. That is the purpose of a calibration. That is a reference point, right? A reference point is also the external version. So me having a calibration weight, I go over to the balance, and I'll put this calibration weight on the balance pan, and I tell it, this is me putting that mass onto the balance. I want you to calibrate against that. See if I get a different value. So everything needs reference points. They just can't make these numbers up. So in the pH world and in the pH probeware, there is not just an ion selective electrode, but there is also an ERE. And the E stands for external, and the R stands for reference, and the second E stands for electrode. An external reference electrode, ERE. Okay, so now what that means, if I think about this in terms of batteries and galvanic cells, well, we've got two compartments. One compartment I know is an ISE, And the other compartment is an ERE, where one is the ion selective measuring device and one is the external reference. So does ISE always get written over on the left and the ERE always get written on the right? No, 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 no. That's not what I'm talking about. All right. So because of that, I'm just going to erase these out of there. And I'm going to put, there is one component and two components, two containers, I guess. Two separate areas. And these areas must include an ISE, which is doing the measuring, and the ERE, which is the reference. How that's done is up to the manufacturer. There were points in time, many years ago, that we had pH meters, and the pH meter would give me the value here, right? And then we would have some type of cable coming from the meter. And nowadays, what happens is that one cable leads into the probe, and that's really it, right? I dunk that one probe into my solution, and then I just wait, and then that number shows up on the display screen, and that's the number that I write down. Okay, well, the problem is that this is very convenient. It used to not be this way, because pH meters were like everything else. They needed a reference point. So actually, the old versions of pH meters, they really needed two probes. One probe was an ISE, and the other probe was an ERE. We had to keep the two chambers separate from each other. We had two containers that we were using in a laboratory. One of the probes would be dipped down into my sample, and this is what I would read. The other probe would be dipped down into some type of reference solution. So I'm going to call this a blank solution. Even though it really wasn't blank, there was stuff in there. But it gave me a reference point, and that's why we called it the external reference electrode. Well, that means that every single time I had to do a measurement with the pH meter, I had to make sure that this probe was cleaned and taken care of and placed into this reference solution. And I had to make sure that this probe was also clean and taken care of and placed into my sample solution. And now I'm worrying about two probes, right? And what if I damage one but not the other? Things still had to be replaced. My meters weren't working the right way. This was a mess. But for the longest time, pH probes were built this way. They were two component probes. Some ISEs, depending on what you're using, still require that setup. Depending on the manufacturer, depending on the ISE that you have chosen to use, they still need a setup very similar to this. And it's okay. Right? A lot of those are not very common. A lot of those are not heavily used in a laboratory environment. That's why they've never really made the motion to just reinvent the wheel. But for a pH meter that is often used so many times throughout a day, with so many people of different backgrounds using it, they had to make this a little bit more convenient. So they took this concept of two probes, an ISE and an ERE, and they combined them into one. So someone, engineering, manufacturing, chemistry, said, let's get rid of this. This is a lot of trouble. It's another probe, more solutions, things I got to worry about. So we're going to get rid of it. Sorry, there it goes. We no longer need this. And this is how a modern pH meter is now made. So what that means is that those two components, again, think of two containers in a galvanic cell, have now been combined into one. And this is called a combined electrode. That's what that is. So in modern day pH meters, that probe does have two containers, like a galvanic cell. There is an ISE on the inside of that probe, and there is an ERE on the inside of that probe. They're all designed this way pretty much now. It's very convenient. It's cheap to make. The science has been there for years. We don't really expect anything any different than that combined probe or that combined electrode. All right. So this is one of the reasons that this throws people for a loop, because they're like, why did you go through this whole discussion with two cells and two containers and two beakers and two solutions and blah, 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 everything two. And that's because this probe is actually two containers built into one measuring device. That's what that is. That's how it works. And again, I want to say that this is the probe and this is the meter. That is going to convert the voltage from those wires. Money, 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 money. Right? I mean, one probe gives off the electrons or the money, and the other probe takes in the electrons or the money. That generates voltage. That meter is going to pick that up now. So within this probe, the same concept of a galvanic cell is happening. Something's going on in a measuring device that's generating some voltage. There's two containers, two solutions, two wires, and that's generating voltage to be given to that meter. So ISE and EREs. Next up, I also don't want you to forget about the idea that pH is really kind of related in a way to temperature. So I'm not going to actually use that sign. That means directly proportional. So I'm just going to say related in some form or fashion to temperature. That means if this changes, the pH will change as well. And I'm not going to go into that theory a lot, really. I just need you to understand that it is temperature dependent. And this pH value needs to be corrected, because a lot of the pH values that we do in a laboratory are taken at a certain temperature of whatever the room is, right? So what if I'm working in a room that's super, super cold, 65 degrees? Or what if I'm working in a room that's very hot and we're up to like 80 degrees instead, or 85 degrees? That's going to change my pH reading, right? It changes the whole dynamic of how this thing kind of operates. Maybe slightly, but it's still going to change it. So for that reason, a correction factor has to be applied. But this is okay because most meters do that for you nowadays. Okay, so what that means is that with these meters, they will often have built-in thermometers. Some type of temperature sensor. That's what we're going to see on the meters. So what's happening is that the meter is getting the voltage that's getting created from the probe, and it also gets a temperature readout that's coming from your room. And it says, well, I'm going to do the math for you. I'm going to be your best friend, and you're going to cheat off of me with my math test. And that meter says, yeah, all right, you can do that. Here you go. So it does the math work for you, and it says, all right, based on the temperature of the reading, based on the voltage that you provided me, we're going to quickly cha-cha-cha-cha, and then we're going to pop out a number, and the pH reading that you're getting on the meter is very often self-corrected already. Very few meters nowadays, even the cheapest of the cheap, very few meters do not have built-in temperature sensors or thermometers. Most of them do. Most of them correct. Even the little cheap $100, $200 ones on Amazon will often have this option. So you don't need to be crazy with the pH meter to get that little bitty fix of a math problem, because they know people just don't want to deal with math, right? I mean, that's kind of a laboratory environment too. The least math that we see, the happier we're going to be. So here we go. Another encounter of technology, ta-da, doing it for us. All right, so ISEs, EREs, the purpose of the meter, and automated temperature correction. Now, we just discussed this concept of a galvanic cell. We just said, you know what? There's two half cells. Those half cells are oxidation and reduction. They're connected by a wire. The wire generates voltage. One side's losing electrons. One side's gaining electrons. We get this whole dynamic that begins to take place, but it's two half cells. Leo goes, grrr, right? Well, here is the galvanic cell in the probe. That's what this looks like. That's why I just spent 2 videos, probably an hour or more, talking about the setup of a galvanic cell. So let's look at this for a minute. Okay. So up here at the very top, we see some wires. Oh, well, I guess I know what the wires are for. Those wires will give me the electron flow that will then equal to the voltage that will then go to the meter. Thank you. Okay. Well, what were those wires connected to? Those wires were connected to strips of metal in our galvanic diagram, right? Some type of metal piece, a metal strip, a metal wire, something. That's what was there. Well, okay, look. Here is one wire into one compartment, and here is another wire that goes into the other compartment. Again, keep in mind, I told you a probe is a combined probe. A ISE and a ERE is present. There are 2 containers that are going to be present inside of this probe, and there's the location of each one of them. So one is in the inner diameter of the probe. I mean, I see that, right? This has no like blue solution in it. This is this grayish solution that they have filled here into that. There's my container number 1. Now, I'm not saying the left hand or the right hand side, but there's one of my containers. And that container, guess what, has solution in it. I see that right up there. It is. It's filled with something. And then guess what? That container has a metal probe that goes down on the inside of it. It's just not a metal strip. It's a little bitty wire. The basics of galvanic is right there. Okay, well, the second component, what is that? Well, this goes around, because think of this probe as 3-dimensional. It's not really depicted 3-dimensional here, but it's a 3-dimensional object, right? It's real life. So the inner chamber has one of my compartments, and then surrounding that chamber is my second container. And that second container is going to have, guess what? A solution, and that solution is kind of depicted here as blue. And that container has a metal strip. There's a wire that goes on the inside. And that's the other half of the galvanic cell. 2 compartments, 2 solutions, 2 wires. Generating a voltage, but they can only generate a voltage if they are somehow connected to each other, right? I mean, that was the purpose of the salt bridge. So if I go back to that diagram that we did, here's the salt bridge, and we said, folks, don't forget, gimme, 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 gimme can only happen so much, because a salt bridge has to go in and it has to do something at some point in time. The left-hand side here is going to run out of money. The left-hand side is going to run out of electrons. You got to kind of keep replacing as needed. So they have to come into contact in some form or fashion. Not really physical contact with each other, but there's got to be something there that allows them to interact and keep exchanging the electrons. That salt bridge is also in this picture. And that salt bridge is right here. Right there. Oh, little porous plug. A little porous plug is a salt bridge. Ta-da! Galvanic. Completed. So what that means is that that area, that porous plug, that area allows interaction between the reference and the measuring probe. Which one's which? Let me clean this up a little bit. We'll delete that. We'll delete this. Get rid of these red marks. I've been scribbling all over the place. All right. So, this one here in the middle, the inner tube, right? This inner tube that's filled with solution that has this metal wire on the inside. This, if you look, has a typical shape of what you would see with a pH probe. Kind of rounded here on the end. This is going to come in contact with the solution. This is the ISE. That is the ion-specific electrode, or AKA the measuring electrode, right there. Notice the other one's kind of chopped off, right? The one with the blue solution that's filled in. So I've got this tube, and then that's inserted inside of a bigger tube that has solution and it surrounds it. They don't come in contact with each other, but it just surrounds it. That's not coming in contact with my solution at all. Period. It's chopped off. It's sealed up. The only way that it's coming in contact is through this little porous plug right there. But this is not doing any kind of measurement at all. And this is our reference solution. And that is our ERE. That is the external reference electrode. Now, we are eventually going to get to a point that we're going to talk about what these solutions are really, and what these metal wires are really. Right now, it's just general overview and how this connects to the electrochemistry world. So my ISE is in the middle. The ISE is the piece that has this bulb that we're always cleaning off in a laboratory, that we're always kind of wiping and patting dry in a laboratory, that we're always dunking this into storage solution in a laboratory. That's what this is right here at the very bottom. That is my ISE. The ERE is everything that's around it. That is my reference electrode. That is, in a way, what it's comparing the numbers against. That's what that one's for. At the same time, I just kind of want to give you a heads up. This ISE here, it's almost every single time made of glass. The majority of the probe does not have to be made of glass as far as what you touch, what you feel, what you see on the outside of the probe. It could be plastic. That's fine. But the ISE tip, that little bitty exposed bulb at the very bottom that goes into your solution to measure it, that almost every single time is made up of glass. So even though these probes might be all glass, they could have a plastic surrounding. They are still deemed as also a glass electrode because it mainly is. And that measuring piece is almost every single time glass for a pH probe to work. All right, so more terms. We're finally connecting the pieces and connecting the dots maybe. So in the next video, we'll pick up with this diagram and we'll talk about these solutions, and we'll talk about these these electrodes and these pieces of metal that make this thing kind of do its job, and kind of maybe begin learning how to use this thing, right? How to keep it clean, how to keep it working, what's going to happen throughout the time of me having it and using it on a daily basis maybe. So those are going to be some of the topics that will show up either in the next video or some of the videos a little bit later on. So, once again, welcome to the world of pH meters and pH probes, just spun in the point of view of electrochemistry.